Okay, so welcome everybody to this new installment of the European Tensor Network Colloquia. So this semester we will have a completely different format. We invited very distinguished speakers to give overview talks, colloquial type of talks about the most interesting and developments that have happened in the field of tensor networks. And it's a great pleasure to introduce Matt Hastings for the first installment of this. So to introduce Matt is actually not very difficult. So if I think about Matt, I actually think about people that changed everything. I think about people like Archimedes, that kind of were able to prove that the surface and the circumference of a circle are related to the same constant pi. I think about Newton, who kind of understood that an apple falling and planets attracting each other, this is all the same thing. And then there is Matt, who kind of came and understood that Lieb-Robinson bounds for static and dynamic problems are all connected to each other. So it's an amazing pleasure to be able to introduce Matt for this series, and we have very high expectations, Matt.
Okay, thank you. I don't think there's any way I can live up to that introduction. But, I'll do my best. So let me just say, you know, these Zoom talks, I would really love it if people would interrupt as much as they can, because it is very hard to know, you know, what people are thinking or whether they're following or whatever, because you usually can't see their faces. I can only see a few faces right now. So please interrupt with lots of questions. This will be an informal Blackboard talk. So yeah, please interrupt as much as you can. And also let me say, you know, getting more into quantum information for me was kind of around 2007 that I started meeting people like Frank and also Norbert and Tobias Osborne and a lot of these people. And it seemed like we kept going to the same meetings every few months. And I remember Frank, every like 3 months, he would give a talk and he would have a new result he was excited about. And he would give like all his previous talks and then add the new one on at the end. And so, you know, there's more and more got compressed in. But somehow I always finished inspired by his talks. So I thought they were great. Like they were the most inspirational talks I heard. So I'm going to try, although I will probably not succeed, to do something similar. I'm going to talk about a bunch of things. So rather than one 60-minute talk, you may think that this is like 3 20-minute talks or something. I'll talk about a few different things, and hopefully it will make some sense, and hopefully people will ask questions. So first thing I will talk about will be some problems in mathematical physics, explaining Lieb-Robinson bounds and explaining some of what they have to do with statics, like exponential clustering, and then talk a little bit about application of Lieb-Robinson bounds in a totally different setting to simulation algorithms for quantum systems. We have both classical and quantum algorithms. And then finally talks about some stuff that's really directly related to tensor networks and Mera states, matrix product states, and so on. And that'll maybe be something that'll be interesting. So if you get confused in any one part, don't worry, there's 3 parts. So, okay. So the whole focus of this talk is going to be, and this is all, like I said, Blackboard, so I'm just drawing, it will be quantum systems on a lattice. So you can imagine, you know, where I draw a point, a vertex, could be like a regular lattice in 2 dimensions, like a square lattice, like I'm drawing here, or it could be some, you know, 1-dimensional lattice or whatever. Doesn't need to be a regular lattice or anything like that. Whenever I draw a site, what you imagine is there's a finite dimensional Hilbert space with each site, like a qubit or a qtrid or something like that. On every site, there's a finite dimensional Hilbert space. And then you have a Hamiltonian, and the Hamiltonian is going to be a sum of local terms. So I'll write it, H, capital H will be the Hamiltonian. Each of these little h will be a local term, and h of x will be supported on some set x. So it'll be a sum of terms supported on different sets. And the interesting case will be that there's some kind of locality bound expressed that these local terms in the Hamiltonian, these little h of x, are all sort of short range. You know, the strictest thing you might imagine, you'll imagine that there's some metric on this space, like, you know, perhaps like the distance between neighboring points on this graph is, on this lattice, is 1 or something. You pick some metric on it. The sort of like the simplest case that's interesting, and of course you can talk weaker kinds of decay, might be that, for example, all the x's have diameter and all these little h of x's have some bounded strength. And when I write 2 vertical lines, that's the operator norm. It's the largest eigenvalue of a matrix. So the case is, so for example, like if you have a Hamiltonian on a line and it's a sum of terms that are nearest neighbor, then R is 1, because they're only one apart, and whatever J will be like a strength of the interaction. So R is a measure of distance, J is a measure of strength. Subject to these, if given these conditions, or given much weaker conditions involving like exponential decay of the norm as a function of the diameter and so on, and I won't go into all the conditions, yeah, there's been all kinds of different work on it, but subject to these, you can often prove some kind of bound called a Lieb-Robinson bound on the velocity of excitations. And what we mean by that is that if you take some operator O, which will be imagined to be supported on some set, perhaps it's supported on some single site or perhaps some small set. And when I write O of t, what I mean always is the Heisenberg evolution of O of t. It means the operator O at time t. So it means e to the I h of t, O e to the minus I h of t. So the Lieb-Robinson bounds express this intuitive idea that if you have an operator O that's initially supported on some set, O of t will spread and will be supported on larger and larger sets, but there's some velocity at which it spreads. And the general form of all the Lieb-Robinson bounds is roughly, and I'm going to be, throughout this talk, I'm going to be totally sloppy about all the analysis. You know, this subject has a lot of error bounds. You're often proving, well, this is exponentially small, this is polynomially, and whatever. It would get things bogged down. So I'm just going to say this is small and try and give hints as to how small it is. But the general form of the Lieb-Robinson bounds is often that there's a velocity VLR for Lieb-Robinson. And in this case, on dimensional grounds, you can guess that it might be proportional to a distance times a time, and a time is a distance divided by a time, it's a velocity, or so a distance times an energy. That's the units it would have to have. And it has some constants that will depend upon like geometry of the lattice and so on. There's a velocity such that if initially O is supported on some set X, so let's say O is supported on X, O of t is approximately supported, let's say approximately supported, on a ball, let's say within distance VLR times t of X. So if initially it was supported on a certain set, it gets supported on a set that's larger by this VLR times t. What do I mean approximately supported? It means like you can approximate it by an operator there up to exponentially small error, exponentially small in time, or if you allow the radius at which you say, okay, instead of approximating on a distance, you know, if VLR is 1 and t is 10, instead of approximating on a distance 10, you approximate on a slightly larger distance like 11 or 12, the approximation gets exponentially better. So this is a kind of general statement you can often prove about this dynamics. It's never going to be true exactly, or except in some very degenerate circumstances but there'll always be a little bit of exponentially small leakage. But you can think of this as a non-relativistic analog of the light cone in relativistic quantum mechanics, that there's some approximate bound on which things spread, and the leakage outside of this approximate bound is exponentially small. And this is a statement about dynamics, but it has a lot of application to statics. And if you want to prove things about the static properties of a system. So let me give a typical result, one of the simplest ones you can prove. It's suppose, and again, I'm being very sloppy about all the precise statements here because this is just to give the overview. Suppose you have a Hamiltonian. H, you have a Hamiltonian H that's local. It has a Lieb-Robinson bound, I won't write it. And it has a unique ground state. You can do the more complicated case with a degenerate ground state, but I'm just gonna skip that. It's really no harder, but I'm just doing it for simplicity of this. And a gap, and a gap, and a gap delta. What does it mean, a gap? A spectral gap, so that the energy difference between the ground state and the first excited state is at least some delta. Then what you can prove is an exponential decay of connected correlations, meaning that if you have two operators, A and B, supported on two sets like X and Y, which are far apart from each other, the correlation is exponentially small in how far apart they are. This is kind of an intuitive statement that's familiar from relativistic field theory, that if you have a gap, then you have exponential decay in the time direction, and because of that, you would expect also an exponential decay at you have an exponential decay in the time direction at imaginary time, so you also expect an exponential decay in the space direction. So you would expect a similar thing here. And so the statement that you would make is that if you look at, say, A, let's say A is supported on X, B is supported on Y, and you subtract off their expectation in the ground state. And there's a slightly more complicated, but not much more complicated form if there's degenerate ground states. And here when I write these angle, I just mean expectation in the ground state of the system. But this is exponentially small. So it will be, in absolute value, it will be bounded by something exponentially small in the distance between X and Y divided by some correlation length. That correlation length will involve the energy gap, delta, divided by the Lieb-Robinson bound, and actually there's a factor 2 in there. And then there's a bunch of other junk that I'm not going to write. It's, multiplied by the operator norm of A times the operator norm of B times some, other stuff too that I'm leaving out. But there's this, minus. So it's exponentially small. The bigger the gap is, the faster the decay is. This is a very natural statement, but how do you prove it? The way you prove this kind of statement is, well, let's just first subtract off constants so that A and B both have vanishing expectation value in the ground state. So I just can get rid of that. And now we want to prove some exponential decay for this quantity. Well, suppose I defined B plus to be the positive energy part of B. Positive energy part of B. Now, what do I mean by that? By the positive energy part of B. Well, what I mean is if you work in an eigenbasis of H, so you have some, H has some eigenvectors, psi sub I with eigenvalues E sub I, then B has some matrix elements in that basis, Bij, which will be like just we're talking about finite systems here. Everything, kind of the philosophy of how I'm talking is here, is everything's going to be a finite system, but finite but large. We're interested in bounds that are well behaved as the system size tends to infinity, but you keep all these interaction strength, interaction range, and so on fixed. So B is just some matrix on every finite system. In an eigenbasis of H, it has some eigenvalues, and B plus will have matrix elements if EI is greater than EJ, and it will be 0 if EI is less than EJ, and say it's a half of what it is if it's EI equals EJ. Again, we'll skip that for the moment. Meaning, whenever B raises the energy, B plus has the same eigenvalues, but it has the other ones as 0 when you lower. So if you wrote a matrix and you ordered the eigenvalues by energy, B plus just contains like the upper triangular part of B. So now we want to compute this expectation value, and I'm going to stop writing the subscripts X and Y just for simplicity. This expectation value AB. Well, this expectation value AB is the same as the expectation value of AB plus. Why is that? Well, you start in the ground state, and so you can only go up in energy from there. But then that is the same as the expectation value of the commutator of A with B plus. Because the expectation value of B plus A vanishes because, well, B plus only raises an energy and you can't raise an energy to get to ground state. So think about that for a second. Expectation value, expectation value B plus A vanishes. So you've explained and given an expectation value in terms of a commutator. And this is a lot like what you might see in free field theory, where you normally order something and you sort of push the creation operators like to one side and the annihilation, push the creation operators to the right and the annihilation operators to the left. Now, where do Lieb-Robinson bounds come in? Lieb-Robinson bounds come in, well, suppose you tried to write down what B plus is. Well, B plus, like here's a guess, and this is not intended to be formally precise. This is thus far heuristic, but then you make it a little precise. 1 over 2 pi integral dt B of t, remember this B of t is the Heisenberg evolution, and 1 over either t plus I epsilon or t minus I epsilon. I'm going to get the sign wrong. So what this is doing is, if you look at B of t is between eigenstates EI with energies EI and EJ. B of t is oscillating at a frequency which is EI minus EJ. And what this is here is like a contour integral that just picks out, it's the contour integral for like the step function. It's the contour integral that picks out 1 if the energy is going up and 0 if the energy is going down. So this is kind of a form, we have to be a little careful to define exactly what we mean by this contour integral. But this is kind of a contour integral that defines what we mean by B plus. You're picking out the positive frequency part by an integral. And we can then, we'll define B tilde plus to be this contour integral smoothed out somewhat, t squared times some I forget what we'll call it. We'll just say, let me just say A, some scalar A. So it will be, this counter-interval will cut off in some Gaussian way. So we'll only include the small times. So B will be this integral over all time. B plus is this integral over all time. And B tilde plus is this integral where you've kind of cut off the time in Gaussian. And if you ask what that B tilde plus looks like, well, if you draw a step function, that's a step function. Here's energy 0. B tilde plus is going to kind of follow it and then start to come down. Sorry, I have a really tough time drawing. I'm not having trouble with my hand staying still. It's just hard for me to draw straight lines on the vertical screen like this. That's supposed to be a smooth line curving down, sort of taking that step function and like curving it into a nice smooth line. That's sort of what B tilde plus would look like. That is, instead of, if you have a matrix element of B that's jumping from one energy to another, and you get either 1 or 0, depending upon whether the energy is increasing or not, here you get something that's quite small if the energy is, if you're over here where the energy is negative, and quite close to 1 if the energy is 1. This x-axis is the energy difference between states. So this B tilde plus kind of smoothly interpolates. And now you play a game. The game you play is you make this Gaussian wide enough that the difference between these two functions is quite small when the energy is at least the energy gap, because you always know that the relevant eigenstates are differ at least energy delta E above the ground state. And that gives you an approximation to B plus that's pretty good enough for your circumstances, and involves just short range in time. Then you take the Lieb-Robinson bound and you say, okay, so this integral is cut off very strongly at large t, so we only need to focus on some small t. In that small t, if initially B was here, it only spreads out in some distance. And within that distance, it commutes with A. So, right, so here's the idea. Here's B, here's A. We had B plus as some big mess, but then we have an approximation to B plus, which is good enough for us, where it's only spread out a certain amount, and that certain amount isn't enough to hit A. And so we use a combination of Lieb-Robinson bound, Fourier analysis, and spectral gap to put all these things together. If you want to think about it in field theory language, what we're doing is it's some kind of standard relation between like retarded Green's functions, which involve commutator, and equal time Green's functions, and that's expressed by this integral. And then we're using that these commutators can be bounded using the Lieb-Robinson bound. So that's kind of like a starting point for how a lot of these things go. A lot of these things use this technique of, you assume that there's a spectral gap, you use some Fourier analysis to take that, like working in an eigenbasis of H, to show that with that spectral gap, something that was completely delocalized can actually be well approximated by something that's a short range in time. Use the Lieb-Robinson bound to make that a short range in space, and then you're done. And you can show a lot of things like that. The proof of the Lieb-Schultz-Mattis theorem in higher dimensions, the quantization of the Hall conductance. All these things keep really reusing this same technique in more and more complicated forms. So let me just pause, because that was kind of the first third of it. So if there's any questions, I'm going to then start talking about the use of Lieb-Robinson bounds and simulation odds. But that was just like to give a hint of how it can say something about mathematical physics. No, everyone's happy. Okay, I see a few faces. Okay, okay. So so now let me talk a little bit about using the Lieb-Robinson bound for a simulation algorithm. And this is based on a paper. The algorithm is from a paper from Jungwon Ha, myself, Katari Lo. But in many ways, a lot of the ideas date back to early work of especially Tobias Osborne. Let me first explain this as a quantum algorithm. But one thing that was really exciting to me was to hear that someone told me that they were actually using this basically to do classical simulations, like on a classical computer of quantum systems. And so hopefully that might be of interest to this tensor network audience here. But I'm going to first talk about it just because this is a way to talk about it as a kind of quantum algorithm, an algorithm to be run on a quantum computer to simulate quantum systems on a quantum computer. And then I'll mention why it was also interesting, why it may be useful as a classical algorithm. And actually, so first let me give this result on what it does as a quantum algorithm. Then we'll have to back up and use Lieb-Robinson bounds to explain the algorithm, explain what's going on. Then I'll talk about why it might be useful for a classical algorithm. So we have a quantum system, again, of one of these forms, say local interactions on some lattice in some dimension. And we're interested in building a quantum algorithm to simulate it with a certain number of qubits, n, let me go back to black. N qubits or n sites, let's just say n sites, they might be qubits, n sites for some time t, and up to some error epsilon. So, our goal is to do this. So what it should be then is something that takes a state. The state should be perhaps represented in a Hilbert space really in the obvious way. Like maybe if this is a system of qubits, we literally have one qubit in our system for each qubit in the lattice instead of going through some encoding. And it should be something that like takes a quantum state of that system and evolves it forward in time using gates, not just like applying a Hamiltonian and waiting, but rather, because this is assumed to work on some error corrected quantum computer, to use gates to do this. And so this algorithm that I'll talk about is the first algorithm that succeeds in achieving for this a time that's this sort of what you would hope for the scaling. It's proportional to the number of qubits, proportional to the simulation time, up to a polylogarithm, a polynomial in the logarithm in n t on epsilon. And you may say, hey, what is t? T is a time. That's not dimensionless. That's dimensionful, not dimensionless. Let's just set like this strength j of the interaction to 1. So really, you should normalize all the times by the interaction strength. So this algorithm is the first one that succeeds in doing that, really, that the number of gates you need to run it, the time on a quantum computer to run it, is proportional to this, and it can be parallelized too. So this is the result. Now there's all kinds of other algorithms for simulating on a quantum computer. There's, for example, a standard one is Trotter-Suzuki based method. So what a Trotter-Suzuki based method is, let's just imagine we have a Hamiltonian in one dimension. We have a line in one dimension, and we have maybe some nearest neighbor terms in the Hamiltonian. So some terms that involve, every pair of terms, there's every pair of neighboring sites, there's some term in the Hamiltonian. And what you do in a Trotter-Suzuki based method is first you go for a little time on the, let's say, the even terms, which are the ones here, and then you evolve for a very short time under the terms on the odd sites and so on. So you build what looks like a tensor network because first you have a little gate for the evolution under the even Hamiltonian, then you have a little gate for the evolution under the odd Hamiltonian, and so on. And so you do a little bit under this one, a little bit on that one. What you do is use the fact that you can break the Hamiltonian up this way. And when you've broken it up that way, it's a good approximation, and so on. The scaling of these can be made. We weren't completely sure what the correct statement is, but it seemed like it's conjectured that you can make the scaling arbitrarily fast in epsilon. That is, if you use the simplest lowest order Trotter-Suzuki, you get a time that scales as a certain power of epsilon. The smaller epsilon is, the more steps you need, because you need to make your Trotter step shorter and shorter and shorter. But as you make, you can use higher order Trotter methods that make it scale faster in epsilon, but we did not know one that actually was really proven to get it with this linear scaling in n and just polylog in epsilon. There's other more sophisticated, not more sophisticated, completely different methods based on like quantum walks and so on. I shouldn't say one is more, it's just a little more abstract, maybe methods based on quantum walks and so on. But this is this method I'll talk about using Lieb-Robinson bounds. It's first I know that achieves that. And the basic idea, well, it works in any dimension, but let me write it down in one dimension. The basic idea is that you can accomplish the simulation in a certain way. What you do is you break the system up into blocks of a certain size, a certain length, L we'll call it. And so we have these blocks of size L like that. And first you simulate forward in time under a block. So I'll write, let's say, plus to say we're going forward in time. Then you go backward in time on the edge of the blocks like that, minus, minus, minus. You inverse simulate the Hamiltonian on the edge of the blocks. And then you go forward in time on the, like that. Okay, so you have lots of blocks. On each block, you go forward in time. The blocks are decoupled, so you can simulate each block independently. Then you go backward in time on these smaller blocks near the edge. Again, those smaller blocks are decoupled. There's twice as many of them. You can do those independently. Then you go forward in time sort of on these joins of them. If you think about it, you just naively think about like how many times does each term in the Hamiltonian appear? It's the right number, because when you look at it, first each term gets, here a certain amount forward, then here a certain amount back, and then here a certain amount forward. So each term goes the right total number of times. But you might go one, why is this mathematically a correct simulation algorithm? And two, what does this gain us? Well, what this gains us is that we can take the size of these blocks, L, to be logarithmic in, we're going to go just for a time 1, and then you can iterate this forward. Time 1, if you want to go to time 100, you do this algorithm 100 times. You make the size of these blocks logarithmic in NT on epsilon. And T will be the final time, the time you're going to need to evolve this. And we'll show that there's an error in the simulation algorithm that's then exponentially small in that L. And so the total error when you put all the blocks together and so on will be exactly what you want it to be. So the error will be exponentially small in the log. So the error will be epsilon divided by NT, and then you put the NT blocks together and the total error will be epsilon as you want. So that's the Lieb-Robinson bounds to show that this L is big enough. And then in each of these blocks, you can use other simulation algorithms which exist in the literature, which succeed in doing things not linear in n, but so there are simulation algorithms that take a time n squared or n cubed or something. And so here in each of these blocks, n, the number of qubits is only this L, which is only logarithmically big. So you can use other quantum simulation algorithms already in the literature in each of these blocks. So using a different method in each block, and then you put the blocks together this way using the Lieb-Robinson bounds. And I'll explain to you how you do it in more than one dimension too. So why is this correct? Before showing that it's correct, let me just give like a completely heuristic way of thinking about it. You could imagine, and this is not right, but you can imagine inside each of these blocks building a little tensor network along the lines of those Trotter-Suzuki things, like a lot of little even bond evolution, a lot of little odd bond evolution, a lot of little even bond evolution, and so on. Fill those blocks with tensor networks. Then you could realize that right here, you could cancel part of this tensor network against part of this tensor network, because like right near the edge here, there's a little gate that evolves forward, and then the same gate evolves backwards. And you can actually sort of cancel part of it here against part of it here. You can't really cancel stuff here because it's too far away and it starts to feel that there's that other boundary off to the right in there. But you can do all that cancellation of gates. You can cancel, and then similarly, you can cancel gates here against gates here. And then you can cancel gates here against gates here. And then what you're left with is just exactly the original tensor network, kind of all these things that I've scribbled over have gone out, and then this top one here drops down onto the bottom one. You're left with the original tensor network. But this is completely non-rigorous. The tensor networks get polynomial errors when you do it this way instead of logarithmic. So how do we really show that this works? Well, let's just go to a simple case. Suppose we have a system made of 2 parts, A and B, and the Hamiltonian is a sum of terms, H equals HA, which will be some sum of local terms, plus HB, which will be some of local terms in B. So A will be a string of sites, B will be a string of sites, plus some HAB, okay, which will be like, say, a little term that involves the rightmost term in A and the leftmost term in B, coupled to each other. So this is a Hamiltonian that we have. And so you want to write down, e to the minus I HT. Well, a standard thing going to the interaction representation, it's called, would be to say that this is e to the minus I HAT, e to the minus I HBT. These two things commute with each other, so I could write them in either order, the AB evolution. And then I have to fix it up. I have the term on the boundary. And the term on the boundary, this is a little bit of a mess to write. So we're going to do, it's going to be the time-ordered exponential, the integral from 0 to 1, HAB, oh, there's an I there, HAB at S ds, or from 0 to t, say. So you're integrating over where this, the times that this intervening Hamiltonian appears at. So the intervening term HAB, so it can get inserted at all these different times from 0 to t, and you have a time-ordered exponential. And this HAB of S is, this is slightly bad notation, I mean evolution under the combined HA plus HB. So you're treating like HA and HB as a free part and HAB as an interacting part. This is the interaction representation in quantum mechanics. And now we can use Lieb-Robinson bounds. We can say this HAB of S, well, HA and HB are both local. So HAB of S only spreads out a certain distance. It spreads out like some here within that time t. So we can say, okay, HAB of S is supported within some distance here. So I don't really know what this is, but it's an exponential, it's a unitary that's supported near here because it's an exponential of an operator that's supported near here. There's some unitary supported near that boundary that fixes it up. You evolve under A, you evolve under B, and then you have a fix up in between. Because it's evolving this, this interaction representation. Wherever this perturbation HAB occurs, it can only spread out a certain amount. Okay, so we've at least guessed that the evolution should be expressed. This starts to look like the picture I drew, these forward blocks, and then some fix up. But how do I argue that the fix up is this backward block on the in between and then the overall forward? Okay, so what I've got is these two forward evolution under here, and then I've got who knows what that is, right? How do I argue that this is equal to backwards on these two blocks and then forward on the joint block? How do I argue that it's that? Well, the easiest way to argue that is to realize that whatever this fix up thing is, it doesn't know anything about the Hamiltonians HA and HB more than a distance, this distance given by the Lieb-Robinson bound away from the boundary. It doesn't matter what that Hamiltonian is because the operator only spreads a certain amount, so it can't start to see the Hamiltonian far away. So if I want to compute what that fix-up thing is, I might as well pretend that HA and HB stop exactly there. That's all they do. So in which case, the evolution would be just the forward evolution in those two regions. So it's evolve forward on this region, evolve forward on that region, and then do some fix up. But we know the fix up has to be exactly undo that forward evolution and then do the correct combined evolution. Hope that makes sense. Did that make sense? Frank's nodding. Norbert's nodding slowly. Norbert's nodding more. Good. Okay, so this is sort of how you do one fix up. And of course you could do this all the way along the system, have a lot of little intervals, undo the evolution on the boundary of each one, and then join them together. And this is a way of doing the evolution in one dimension. And this gives you this simulation algorithm. If you want to do it in higher dimensions, you can do a similar thing. What you can do is you can take 2 dimensions, for example, hexagonal lattice and a big hexagon. When I say big, what I mean is, can people hear me okay? I just saw that it says my internet connection is a little unstable. I might need to move closer to the router. So we draw a hexagonal lattice and we're going to color them different colors. Like we color this one red, we color some of them black, for example, and we color them white. So like we 3-color the, in yellow, for example, red, black, and yellow. So and then you can, keep on going. So then over here will be a red one and so on. So you 3-color it, and each of these hexagons will be big. It will be this size L, this logarithmically large size. And then what you first do is you want to build up, say, the red evolution. So you evolve within the red cells. Then you want to do combined red and black. Our goal is to build the combined evolution under the sum of the red and black Hamiltonian. So we do exactly what we did in one dimension. So we evolve under the red, we do some unevolution near the border, and then we do forward evolution in all the black cells, and that builds up that. Then we need to add in the yellow cells, and that requires some unevolution near the boundary of each yellow cell, and then doing a forward evolution under the combined thing. And so in this way, the number of layers of this construction goes up proportional to the dimension. And so, assuming you can build these, find these tessellations. So with, you can do this algorithm in any dimension and do the simulation in any dimension. So this is a Lieb-Robinson based simulation algorithm. And it gives some sort of, picture. We had this very kind of simple picture that we had Trotter-Suzuki evolution, which gave us a tensor network. That the tensor network was, for time evolution, was evolve under even bonds and odd bonds, and that this was the tensor network for time evolution. This is a valid tensor network for time evolution. The trouble is that the error goes to 0 only polynomially as the size gets large. So what this kind of picture here is telling us is that we can build another tensor network for time evolution, which looks actually basically the same as this, except each of these blocks here, instead of just being 2 qubits, will be many qubits coming in and many qubits coming out. So, and you just kind of regroup it into blocks of size, instead of each one being 2 qubits in, 2 qubits out. They're like, 10 qubits in, 10 qubits out. But you're still building something that's a tensor network, except the gates now act on like 10 qubits instead of 2 qubits. And by doing this, the gates become more complicated, but the error becomes exponentially small in the size of these. And as I say, so I really want to mention this at this tensor network colloquium. I was really excited, and I'm sorry, I forget the reference, but someone was recently telling me that they found this like useful for classical simulations, because in many classical simulation methods, whether you're simulating brute force time evolution or you're simulating some kind of matrix product state evolution, something that sets a scale is how big a term in the Hamiltonian is. But for these Lieb-Robinson based methods, what sets the complexity is how fast the Lieb-Robinson velocity is. And if you have Hamiltonians where there's some very large terms in the Hamiltonian, but they commute well with other terms, which is not actually that uncommon in physics. I mean, you can easily think of cases where that happens. Then Robinson velocity might be reasonably small, and then you have sort of what you might call like a very stiff equation of motion, but the Lieb-Robinson velocity is not so fast. And so this can actually be useful. So I just, throw it out in case it's useful for anyone. So this is kind of the end of the second piece. So again, let me just pause for any questions. No? Everyone?
Wait, maybe I have one question. Like if you take this approach and you would convert it to a matrix product state, would that be captured?
Well, so this is a matrix product operator here. Yeah.
Right.
I mean, so you'd have to take each of these blocks, and each of these blocks is now like on 10 qubits. So if you wanted to, you would either have to group your qubits into, blocks of 5 or 10 qubits, however many, so you're increasing your site dimension, or you would have to increase your bond dimension enough that you could take this 10 qubit to 10 qubit unitary and express it in terms of, carrying all the information along the bond dimension. But it could be done. And so I'd be very curious if there's cases where it turns out to be useful to kind of think of these kinds of scalings even at a short site. As I say, I was excited to learn that it was useful for at least one person. So I don't know how generally, but yeah, I mean, there's of course a difficulty that you end up having to increase the bond dimension as you do it, but you're always gonna, at the same time, you're also going your time forward. So you're always going to be having a bond dimension increase. So it may depend a lot upon what the velocity it is, what the time you need to evolve for is. I see there's some stuff in chat. Is there someone saying something in?
Right, there's a question in the chat. Can you read it, or shall I read it to you?
Yeah, maybe I missed it because this is assuming this is completely general, like Trotter evolution. So the whole point of Lieb-Robinson bounds is there are statements about operator norms. There's statements that the operator is well approximated by a local operator. And so that means regardless of what state you evaluate that operator in, if the error is small, because if whatever quantum state, if you give me an operator and say, what's its expectation value? Of course, it's going to depend upon the quantum state. But if you tell me the operator norm of that operator is 10 to the minus 10, its expectation value is at most 10 to the minus 10 in any quantum state. So, and these bounds are all about these kind of operator norm bounds. And then that operator norm bound, using this interaction representation and so on, is promoted to like a bound in, well, these unitaries that describe, this gate evolution is close in operator norm. So no, it doesn't assume anything. It is general like Trotter decomposition. It's a good question.
So Matt actually had a similar question. So it means that actually for the same error as you would make with the Trotter error, you can make much bigger time steps. Is that correct?
Potentially, but then yeah, you also need to increase the size of your blocks from whatever they are to something bigger. Yeah. And whether this will pay off, but I can sort of really see that this could pay off because Trotter always comes with like a naive light cone. There's a naive light cone in Trotter because each of these gates, only spreads at most distance 1, but then your light cone with Trotter is proportional to your inverse time step. Whereas here, the light cone is just, it's really the Lieb-Robinson light cone. So it's getting the correct one. So, obviously, implementing this kind of thing can run into a lot of difficulties because you start needing to have these evolution on these bigger gates, and on a quantum computer you can do that. So I don't know how much in practice, but I was, let's say at least one person found it useful in practice on a classical computer. But yeah, it'll depend, a lot on what the Lieb-Robinson velocity is, what time you want to simulate. But potentially, like if you have a system with a large time but a small Lieb-Robinson velocity, this may be the way to go. Okay, There's another question. What is this here? I have a general conceptual question. Entanglement always follows from a lack of information in some sense. Which path information? Would it be correct to say that, yeah, I mean, this is, again, yeah, this is sort of immune from entanglement. One way of thinking of the Lieb-Robinson bound is that it's, it describes a response to this paper of mine with Frank and Sergey. This was Frank's idea. So we should say this is Frank's, that the Lieb-Robinson bound says like the response to something. So if you have a system and you do something, doing something to it is applying some unitary to the system, making some transformation, and you can ask how far away can the effect of that unitary be felt if you try to communicate. And the Lieb-Robinson bound says like this is how quickly anyone can feel the response to some unitary being applied somewhere. Okay, more questions? No. Okay, so the last thing, and this is going to be really related to tensor networks, is to talk about area law. So suppose you have a quantum system in one dimension, and I guess because this is the tensor network community, I don't need to say what is a matrix product state. If anyone wants, I will, but I think people probably know in this talk. So let's say each of these here is, these are some, and each of these vertices is some three-leg tensor defining the matrix product state. Each of these external legs is some physical degree of freedom, some qubit or qdit or something. And each of these horizontal ones are some bonds. These matrix product states are, of course, fantastically successful in describing many systems in practice, starting with the DMRG algorithm. They're also useful for many theoretical examples, like the AKLT chain. The question is, if you're just giving, why it works, like why, if we're given something that's not one of these theoretical examples, which can we show that the matrix product state will actually describe it well? If you're just given some general gapped Hamiltonian, can we show that a matrix product state will describe it well? So the question really is, one thing about a matrix product state, there's a certain bond dimension on each bond, and you want to keep the bond dimension small because the computer time goes up with it, and the memory goes up as the bond dimension goes up. And the question is, what bond dimension can you get away with in order to make a good approximation to a matrix product state? And this is actually closely related to the entropy of entanglement. So if you take the system and cut it into the left and right part, what you get is that this pure quantum state can be described by some mixed state, a mixed state on the left or a mixed state on the right. And it's a pure state, so you can ask for what is, let's call this left and right. You can ask what is the entanglement entropy on the left state, or you could ask what are the Rayleigh entanglement entropies. So the entanglement entropy, so you have some, will be minus trace rho left log rho left. This is the reduced density matrix on the left, or this is the von Neumann one. There's also Rayleigh ones, which are traces of powers. And as Frank and Ignacio pointed out, that the error could be bounded if you knew a bound on the Rayleigh entanglement entropy for various ones. But generally, there's a close relationship between this entanglement entropy and the needed bond dimension. And then you can prove, in fact, that as long as you have a gapped Hamiltonian, once you've bounded in one dimension, or once you've bounded, in fact, just like any of these entropies, you get the bound on all. You can make up states which have a bounded von Neumann entropy, but don't have a good matrix product state description. But for a gapped Hamiltonian, you can show that can occur. So really, one of the questions in asking if there's a good matrix product state description is, can you bound the von Neumann entropy? This is not necessarily all true in higher dimensions. There's a more difficult question in higher dimensions, but at least in one dimension, this is a big question. And so people talk about an area law. An area law is, if you have a many body system, you look at the entropy of some region. What is its entanglement entropy with the rest? Is it proportional to the area of the boundary of that region? Is it just entangled sort of near the boundary of that region, to put it very loosely? Since this is a one-dimensional system, the boundary of the region is just a point. It's just the end. And so if you have an area law, that means the entanglement entropy is bounded by some constant, in which case a good matrix product state description will exist. So can you prove this? Can you prove, like, just for a general gapped Hamiltonian, that this occurs? So I had a proof in 2007 that used the assumption that you had a gapped Hamiltonian, gapped local Hamiltonian, got some fairly weak bound. One went exponentially in the gap and a bunch of other things. And later this has been improved by a number of different people to something that's only polynomial in 1 over the gap, using, again, the assumption that it's a gapped Hamiltonian. But an interesting question you might ask is it true that if the exponential decay of correlations on its own implies that there's a gap, because that there's an entanglement bound? You know, all these proofs are using the fact that it's the ground state of a many-body Hamiltonian, which is local with a spec gap. But if I just give you a quantum state on a line, and I say this quantum state has exponentially decaying correlation functions, can you prove that there's a bound on the entanglement entropy? And a kind of really naive bound, and this is like totally hand-waving, would be to say, well, so you have some correlation length, and you know, so maybe this is your correlation length C, and only the degrees of freedom within that distance C of the boundary can be correlated with the others. So the entanglement entropy is at most, you know, proportional to the correlation length. This is, of course, not, you know, a completely valid argument, because, you know, entanglement isn't really necessarily like one thing with one thing. It might be some complicated many-body structure. So you can ask, just as a general question, if I write down a tensor network, if I write down a quantum state and I know that the correlation length is bounded, do I know that the entanglement entropy is bounded? So exponential decay, does it imply area law? And I had a paper that said no. And the argument that it said no was based on a random matrix product state. You could write down a random matrix product state, take all the matrices in the matrix product state to be the same. So it's a translation invariant matrix product state, and just select them at random. And by doing this, there's a certain transfer matrix, and you can get a gap for the transfer matrix. And so this old Fanes-Nachterhalle-Werner paper that shows that this gap of the transfer matrix is related to the decay of correlation functions. And if you had that gap in the transfer matrix, the correlation functions decay exponentially. So you can write down this family of matrix product states, and they're literally just random matrix product states, where the correlation functions decay exponentially. And yet it's a family, and you can make the bond dimension bigger and bigger. You can take 100 by 100, 1,000 by 1,000, 10,000 by 10,000, whatever. And so the entanglement is close to maximal. So the entanglement entropy diverges, gets as big as you want in this family, but they all have exponentially decaying correlations, and all with the same bound. You know, you can have like correlation length like 3 or something, and yet correlation on qubits, and yet the entanglement is as big as you want. So the answer is no, right? Then there came a paper of Brandau and Hordecki where they said, well, no, actually the answer is yes. And they have a replicated proof where they prove that in fact exponential decay does imply an area law. And so, you know, did one of the groups of papers make a mistake? Brandau and Hordecki thought that the issue was, well, in the Fanes-Nachterhalle-Werner paper, they were doing something in complete generality, and there can be a prefactor in the exponential decay for arbitrary ones. But so they thought maybe that was the issue. But in fact, that's not the issue. It turns out that for the class of matrix product states we were considering, we can get it so that really there's no prefactor in the exponential decay. So there's really a question. And the reason there's a difference, this is something I just felt like talking about because it's not really explained too well in the literature, is that when I showed no, you can have exponential decay and yet arbitrarily big entanglement, what I was considering is that you have some operator A, which is supported here, some operator B, which is supported here, like there and as far over to the left as you want, and there and as far over to the right as you want, and with some distance L between them, and the entanglement decayed exponentially in that L. That's the thing that comes from these transfer matrix calculations. And I showed, well, if you can have those correlation functions be exponentially decaying and have as much entanglement as you want. If you look at the Brandau-Hordecki paper, they also consider cases where like A is supported on a small interval and B is supported on something that encircles it. And the transfer matrix calculations don't tell you that that decays exponentially. You have to consider a more complicated transfer matrix on a folded thing. So there's this funny situation that does exponential decay imply some kind of area law, even with a very weak bound? And the answer is, well, it depends which correlations you're considering, and you have to consider this one where B sort of sits outside A as well. And I'm just going to kind of go really quickly at the end here. So I started to wonder, well, you know, Brandau and Hordecki had this incredibly weak bound. The entanglement entropy was like 1 over C, sorry, not 1 over C, X could be exponential in the correlation length, not proportional to correlation length, but exponential in the correlation length, much bigger than that naive guess that it might be proportional to correlation length. So you might think, well, did they prove a type bound or not? You know, maybe it was a weakness of the proof, maybe that's really correct. So I started thinking, well, can I make up a state that has all the correlation functions they consider too, also being exponentially decaying, but still has this enormous entanglement entropy? And the answer is you can do it. And rather than considering a random matrix product state, what you want to write down is a random Mera state. So Mera state will have you have some tensors that first are just like unitaries going from something to something all the way along a line. Oops. Then you take these and you sort of reduce dimension. So you take a pair of incoming legs and they go to some to some lower dimensional thing. So these are unitary and these are isometry. So unitaries and isometries, and you move up. And what you've done is you've reproduced a one-dimensional network on a slightly decimated lattice. Well, you removed half the vertices. And then you repeat it again. You then do an entanglement between nearest neighboring ones, and then do one of these isometries to reduce the dimension, entangle between neighboring ones, and isometry to reduce dimension, and so on. You keep going up in this Mera state. That's the definition of a Mera state. And these Mera states have been useful for describing systems in various dimensions. But what you could do is you could write down a random Mera state with very high bond dimension. And you could play some kind of game of trying to balance. You make all these unitaries and isometries random, but you could play some game of balancing like what the bond dimension is. You could allow the bond dimension to decrease very slowly as you went up, so that the isometry from here and here to here, rather than cutting the dimension from, like, say these were both dimension 10 incoming, so they're, instead of going from 10 times 10 to 10, which would be like keeping the bond dimension the same, or going from 10 times 10 to 100, which would be not getting rid of any information under this isometry. You go from like 10 times 10 to like 99. You get rid of a little bit of information on the isometry. And then at the next level, instead of going from 99 times 99 to whatever 99 squared is, you go to like 99 squared minus a little bit. When you play some game of balancing how much information you give up in the isometry as you go up in level, you try to give up as little as you can so that you can get as much entropy as possible, but do it as fast as you can. And what you can do is you can build the state. Now, there's a few things in the paper that are conjecture and aren't proven. Some are relied on, like, well, numerically this seems to happen, but I'm pretty convinced that, here's a way to build a state that gets to that, has all the correlation functions, including the ones that Brendau and Horodecki consider exponentially decaying, and has this exponentially big area law. And in fact, I'm pretty sure, and again, this is still a little bit conjecture, that you can write down a one-dimensional state where the correlation function k is e to the minus L to the 0.99. So not quite exponentially decaying, but as close as you want, and not obey an area law, have arbitrarily big entanglement. And in fact, that you can write down a 2D state where the correlation functions decay is e to the minus, and again, like, this is not all, a lot of this is sort of conjecture, numerical guesswork, and so on, but it seems like, I'm pretty sure it's true, where the correlation functions decay is e to the minus L to the 1.99. So like actually faster than exponential, but not quite Gaussian. You can guess how it goes in higher dimensions, where again, there's no area loss. You can write down some ridiculously entangled tensor network states that come by building up random Mera states. They're in some ways maybe related to these like ADS CFT Mera constructions or something, except with a very different choice of how the bond dimensions go as you move up the tree, instead of, because you're not trying to mimic anything to do with ADS, you're trying to do this thing of like building a highly entangled state where all the correlation functions decay. So I think there's this very interesting question about, correlation is such an easy thing to think about compared to entanglement. And when we want to talk about like many body entanglement, our intuition tells us like, oh, it's short range correlated, so it's got to not be entangled. But we know that there's things like topological order where you can have everything look short range, but there's some global entanglement. But it also seems like there's things where everything can look short range, and yet there's just no area law. There's actually a volume law in the system, and yet the correlation functions are, almost Gaussian decaying, and yet there's a volume law in 2 dimensions, which to me is like a very bizarre class of states. So let me finish here and take any questions.
Thanks a lot, Matt, for this very inspiring talk. Yeah, I'm sure there are questions. So maybe I can start with a small question. So what is the I didn't quite get the big difference between these two definitions of correlation length, the yours and the one of Brandau and Holodecki. So what is the intuition there that they are so different, that they lead to such a different assumptions?
Yeah. Well, what really one is, and this is funny to me, one is this like something on the left and something on the right, and the other is like something in the middle and something on the two sides. And so, when you look at matrix product states, right, a key role is played by this transfer matrix. So you have some matrix product state.
Yeah, but you could.
Oops, sorry.
But if you have an MPS and you would fold it, you would
exactly. Yeah. So you could fold the MPS. But let me get to that in 1 second, okay? So a key role is played by this transfer matrix, and here everything is played by this. When you look at this setting, you can express everything in terms of eigenvalues of the transfer matrix, and in terms of some sort of stationary fixed point, which is the fixed point of this transfer matrix. And when you fold it, things get expressed again in terms of eigenvalues of the transfer matrix, and the eigenvalues are what you'd expect because they're like just two copies of the transfer matrix. But when you fold it, what you are is you're like sitting, so then B is here and A is just on the side when you folded it. So you're now not starting with the like fixed point of the transfer matrix, you're starting with some very particular states. And so the calculation in this Fanis Noether-Werner for the correlation in terms of the transfer matrix, it depends, what the fixed state is and like where you start. And here you don't you don't have that property because of where you start, that you're not starting at this fixed state. You're starting at some very particular state at the edge of the chain. And so this thing enters into what the correlation decay is, that in one case you're starting in the fixed state and it turns out to be a completely uniform fixed state. But when you fold it, you're starting in a state that's not the fixed state, and it's actually like a maximally entangled fixed state between the two things that's in the fold.
Yeah, that's very, very weird.
Yeah, it is weird to me. It is weird to me. I give you, and this may make no sense at all, but like one thing to me that is a way of thinking about it. Imagine you have an expander graph, okay? And an expander graph looks kind of locally like a tree, right? And if you start somewhere and you do a random walk on the expander graph for some number of steps, so you'll tend to just kind of walk away from the origin. You can sometimes take a step back towards it, but you sort of walk away, you very quickly forget where you are. And if after 10 steps you said, oh, I'm over here, it would be very hard to see where you started from. But so if you told me like, I ended here, where did I start? I don't know, somewhere within 10 steps of you, but there's, so many vertices there. But if you said 10 steps in the future, I was here, and 10 steps in the past, I was here, then I know how you went, because there's like a shortest path. So it's a funny thing, like if you think about random walks on an expander graph, if you know like where you are, a minute from now, that doesn't tell you where you are now, it tells you very little. But if you tell me where you are in a minute from now and where you were a minute ago, I can guess that you are on the shortest path between them right now. And I have some fairly good idea where you are. And that's kind of what's going on here with this state, that you have this operator on the left and right, and that's able to give enough information to, when you do that, because all the constructions of these states with like fast exponential decay of correlations, but high entanglement, they involve something like expanders, a quantum version of expanders. And so the point is that in this quantum version of expanders, the operator B on the right doesn't know anything about the operator A on the left, or exponentially little. But the operator B that's on both sides can figure out what is going on in the middle.
Can I ask about, so you explained very convincingly that just saying exponential decay really doesn't cover the richness of ways in which these quantum systems can be correlated. Mm-hmm. And I think you touched upon it, but maybe can you explain what kind of correlations can you have if it actually comes from a gap ground state? I mean, you have not just a proof of exponential decay, but you have expressions for the estimates on the correlations functions. And so many of the things that you introduced in these examples they can't come from a gapped Hamiltonian, or at least not a uniformly bounded one, and so on. So is there a way to succinctly characterize what you will see if you have a gapped Hamiltonian?
Yeah, I mean, I think there's sort of two things to say. One, yeah, I mean, it's certainly, I guess, a lot of work is trying to succinctly characterize what we will see. I mean, in one dimension, we kind of understand it all now. We know that it's matrix product states, and it's now even the bounds are down to polynomial in the gap. Whereas in two dimensions, just even if someone proves an area law in two dimensions, you don't need to get so excited about it, because that doesn't mean there's a tensor network. Even if they prove something about, an area law for Raynier entropy or something like that, that doesn't tell you. So you really would, I mean, of course, I would like to conjecture that there is a good tensor network description with some bounded bond dimension and some, maybe like a certain transfer matrix in the tensor network also is decaying. But, I think if your goal is understanding gapped Hamiltonians, one way to think about this is to say, we're trying to, isolate what's weird when you just talk about correlation. So we know we need something more, but, we don't know what it is. We would like to conjecture this is true in 2D, but we don't know what it is that we don't know what the things we're looking for, other than just conjecturing, oh, they're all tensor networks, PEP states or something of some kind with some extra constraints. Yeah, I don't, I think that's like a big open problem to say what it is. I guess the other way of thinking, so one way of thinking about it is to say that this is like just a way to help shed some light on it by saying like what kind of weird behavior, why like in higher dimensions, really just looking at correlations is definitely not enough. Maybe you need to look at some like multi-scale correlations, because this MERA sort of reveals something about scale. So maybe there's some kind of multi-scale correlation that could be considered that would, that could be added in. If some kind of like this correlation of these two things here with something in the middle that told us like, oh, in 1D, that's a kind of correlation function we should think about. But maybe there's some kind of like multi-scale correlation function we could think about that would be useful in higher dimension. But also I think they're just interesting as exploring like the structure of tensor network states, just as people are interested in exploring ADS toy models, it may be interesting to explore states that seem, highly entangled, seem highly rapid decaying correlation functions, and yet highly entangled. It's like an interesting class of states to think about, and maybe they will find some use in some protocols. I mean, I don't know a use yet. But.
Fascinating. Thanks.
Yeah, sorry, that was kind of a long-winded reply. I mean, it's something I have no answer to. So,
but does one still conjecture that if actually have a short-range Hamiltonian with a gapped ground state, then you expect a good, simple tensor network representation that doesn't need these additional tricks?
Yeah, I would like to conjecture that. I'll go. I mean, that's obviously like the conjecture everyone wants to make. So I will go conjecture that, and that it's. And you say good, simple. I mean, I'm sure what you have in mind is like probably this means something about some transfer matrices and transfer matrices of various things having additional properties too, because bond dimension maybe you can take a PEPS and hide all these things in the PEPS. Like you can build a PEPS that shows the 2D Ising model at criticality or something. So it's probably some extra.
Right. No, yeah. Of course, we would have to have some homogeneity, and then we assume that sort of bond dimension is uniformly bounded and constant.
Yeah. So I would conjecture that. But
okay.
But you also have conjectures when you have indeed non-trivial edge modes. No, if you have chiral edge modes, that this is not possible.
You think there can be no tensor network if there's chiral edge mode?
I don't know, but it feels very much that if you have a tensor network, there will always be something like a frustration-free parent Hamiltonian. That's what you expect.
Yeah, well, okay, then I can make a weaker conjecture, which is that there's a that it's sort of stably true. So, for example, that you can or it is true. Yeah, maybe I shouldn't say stably true, but that like, for example, if you have a certain chiral Hamiltonian, maybe you could add in its complex conjugate and look at like imagine like a bilayer system with one and one and one in the other, and then you could write down a tensor for the join system. So one might be able to, is a good point. Maybe there are some topological obstructions, and it would be great if there, could be proven whether there are in some case, but then I would conjecture that if there are topological obstructions, they can be evaded by considering, adding in other things to cancel them. For example, this can be useful in studying free fermion systems, like perturbations of free fermion systems. If you have some free fermion system, which has some topologically non-trivial band structure, then you can't, like think of it as a frustration-free system, but you can take it and its inverse and then look at the combined system and study it in that way. And that can be useful to prove stability of free Fermi systems by considering the stability of a more general system.
Of course, or there could be a relevant operator close by that opens a gap, and then you could simulate that one and then do some scaling. But that's of course not an exact representation.
Mm-hmm. Yeah, and I mean, probably also one needs to, as you say, one needs to think a lot about like, errors in these representations. What we would be happy with. Like, do we care about? For example, like most of the literature in mathematical physics and computer science has focused on, is there a tensor network representation with approximation error epsilon, as and so as the system size gets big, maybe you need to keep the bond dimension increasing to keep epsilon fixed. Whereas in the physics literature, one is happy if the operators themselves get error, you compute the operators to within error epsilon, and you don't care if actually the wave function approximates the ground state one to error epsilon. So there's different notions of close that would need to be considered.
Okay, so are there other questions? Still many people around, so I'm sure that they want to hear all the answers to all the questions, but so maybe a historical question, Matt. How did you encounter basically these Lieb-Robinson bounds? When did you see that these are such a powerful tools to actually prove static properties, or to use them in proofs, let's say for the correlation length and for all these other wonderful things that you did? So what was the main insight there? Or
I don't know. I mean, I just spent so much. I mean, it was a paper of, I've mentioned this paper before. It was a paper of Claire Lullier and collaborators on the higher dimensional Lieb-Schultz lattice, and it was a numerical paper, but they sort of said this is why we believe it to be true. And I remember reading about that paper, and then I just got kind of obsessed and thought about it for like, okay, how are we going to prove this? And this was, I don't know, you have weird memories. Like I sort of can remember like, I was at a conference in Paris and like walking through a square at night and like remembering like some operators at different times, but you can't really like say where it comes from.
So Matt, so can I ask, so would it be fair to say, so you felt that there really had to exist something like Lieb-Robinson bounds before you were aware that Lieb and Robinson decades ago had actually proved?
Yeah, I mean, actually, the referee told me that that was a known thing, so I didn't know this name. Someone told me the name.
So there was a referee who pointed it out. I see.
Yeah, someone told me, oh, this is Lieb-Robinson. So I didn't know what this was, or maybe it was a referee. Maybe it was like someone I sent it to before it was refereed or something. But I remember someone said, oh, this term is known. I didn't know what this term was. But it's been cool to see like so much. There have been a lot of interesting results on it now, and coming from so many different things, people working on like power law interactions for Lieb-Robinson bounds, or Lieb-Robinson bounds with different kinds of different anyons or whatever. I mean, it's amazing how many different, I can't follow it all now. So much.
So Steve, it's amazing. It's remarkable that for over 30 years, so now it's so obvious how useful this is and how important it is in understanding the structure of many-body states and dynamics. While for 30 years these things existed, and quite a few people knew about the theorem. Mm-hmm. It felt like, that's something interesting and deep, but nobody applied it to solve a problem.
Until, including Lieb, did Lieb ever use it actually for proving anything? Or
no, nobody did. Well, anything. Okay, so some people will be offended probably when I say that, but nothing. I mean, realizing really how central it was and how to use it. That was Matt's big contribution. I think it's, I don't know why nobody saw it. People guess that it has to be something as useful, as important as the finite speed of light in the structure of many body theories, non-relativistic ones, but never couldn't sort of put it together. Well, I guess it's what Frank said, you know. Archimedes, and then I don't know who else it was, but
I see that Steve, do you have a question actually? Because
I do have a question. So I'm not sure how to frame it. Sorry, I missed the first half of your talk. I forgot about the daylight savings time change. Yeah. But so I'm curious about what kind of circuit can create these weirdly strongly entangled states. Like, you know, if you think of local circuits, somehow it seems like you couldn't create them with local circuits. And, you know, how do we think about the circuits that could create them?
Yeah, I mean, like these random Mera ones, like the only circuit I know that creates it is a Mera, but sort of by construction, it's a Mera with ridiculously high bond dimension in there. Because this bond dimension sort of barely drops down as you go up the level of the tree. So it's not a, you know, yeah, it's a finite Mera. So because, you know, if the correlation length is O of 1, then this is, but it's not, and, you know, and maybe a related thing you could wonder, and maybe this is a more mathematical question, is like, and again, none of this was proven, but this was like as a family of states, like you give me a certain correlation length, and here's like what the bond dimension is. And if we look at these things that are almost exponentially decaying, then the correlation can be as big as possible. But is there like truly a many body thing instead of like a single realization at a single size? Can you come up with some like infinite size limit of these? I don't know. And I don't know if there's like any kind of good circuit that does it, because just like random local circuits will tend to scramble things probably too much locally. So I don't know if there's any good way to create them other than this like purely mathematical thing.
So Miras sort of, you know, have the long range components of them sort of right away, and you know, so they can do a lot more than you can do with local gates, at least more quickly.
Right, exactly. But this is like a Mera with a ridiculous bond dimension too, so it wouldn't be so. I mean, you could build a low bond dimension version of this and then create that as a state, but a truly high bond dimension one, or this like, and when I say that, oh, I'm pretty sure that there exist these states that are, you know, e to the minus L to the 0.99, but no bound on the entanglement entropy. That's sort of like, I think there's a family of them that does it, but I don't know. Can you build it like it's directly in the infinite size limits? I don't know. And whether it's, you know, it's a great question. Is there a way to, you know, make these? I don't know. Maybe there's some use. I don't know.
I mean, the other question is, you know, well, can nature make them very well? If you say nature tends to start with, you know, you think about it as starting with some product state and then things happen.
Yeah, I mean, maybe nature can make them naturally on some ADS geometry or something like that, if we were very speculative. I remember trying to ask, I don't know if anyone in the audience is like a high energy expert, because I remember asking, you know, there's all these like ADS CFT Mera constructions, and then related to this like Ryu Takanagi formula. And I was wondering like, okay, here's some other kind of Mera, and is it related to some other physical process? Maybe, you know, does this bond dimension correspond to some geometry where there's like, you know, a black hole at a certain radius, but there's some other thing. I don't know. Yeah, I mean, maybe that would be, I don't know if what I'm saying is relevant to your question, but I was like trying to think of a physical connection, and the only one I could think of was that, but I didn't.
But these states are still very far from random states, I guess, no? So if you would take a big state following the Haar measure, it would not look anything like these Mera states that you have.
Yeah, but then a state with the Haar measure does not have this exponential decay, right? Because if you take a big system and you look at a observable in some finite region near the origin, that observable, you know, this like, look at observable spore within distance 10 of the origin. Well, that's like at any distance, like distance 1,000, it's still like almost perfectly entangled with the stuff outside, right? This is a general property of these random states. You know, maybe I'm not making sense here. Like, so let's say we have like a completely random state, and we draw a very big shell of some radius capital R, And then we lose some little thing of radius little r inside it. And then finally, we have the system, which is some, enormous size, much, much bigger than r. Well, then on a random state, the stuff inside this diameter little r is almost maximally entangled with the stuff outside because it's less than half the dimension of the Hilbert space. And since it's almost maximally entangled, any little piece of it still has all its information reflected outside. So this little block of distant size, little r, is still perfectly entangled with something outside, even ignoring, tracing out all the stuff here. This little blob in the middle is like perfectly entangled with everything outside. So these random states are not exponentially decaying. They're like, you have to go very far away before you start to see it again, but they're not exponentially decaying. Like, you look at this distance little r, this little blob, and it's like completely uncorrelated with everything until you get far enough away, and then it's perfectly correlated with it. So this random state, it's somehow, yeah, you're right. It's not a random state. It's some other kind of state. It has some structure on top of the randomness.
Okay, I think people are very satisfied. I certainly am. Matt, thanks a lot for your great talk, and I hope to see you soon live.
All right, yeah, hopefully at some point after this all calms down. Okay, thanks very much for the invitation. Great to see everyone again.